All right, what's going on, everybody? Today we're going to take a look at wiring batteries together in series and in parallel. What's the difference? Is there an advantage to either? And I'm going to go over just writing out the circuits real quick. And then after we get through this, I'm going to go to the bench and we'll actually wire in a circuit with a light. We'll measure the current and I'll show you the differences. And then at the end of that, I've actually got a thermal gun and we'll take a heat measurement. I'll run each of the setups parallel and in series for 10 minutes, and then I'll come back and we'll take a heat sample and see if there's any advantage. Since it's such a low current circuit, I don't know if we're going to be able to see it or not, but I'm hoping we will. Anyway, let's get into it. So for this particular exercise, I'm going to use two 12 volt, 3 amp hour Milwaukee M12 batteries. Each battery has 36 watt hours. I'm going to use one light. The input is 9 to 30 volts DC, and it's rated at 18 watts. So this is a perfect light to use for this example because we're going to be using 12 volts and 24 volts to get this done. And we'll look at the parallel circuit. The parallel circuit, we are going to run each battery pack side by side. So the important thing to know about parallel and series, and this isn't just for these little drill batteries, this would be for your deep cycle batteries and stuff. I know a lot of people do solar power battery banks and things. Same rules would apply. The biggest things to remember is to use the same battery chemistry when you are turning batteries together. If you do not, that could create a safety hazard. And another serious rule to remember is to either charge these cells together, or in the case of the drill batteries, when you use two of them, just make sure that they are both fully charged. You want them as close to equal as you can, because when you tie them together, the batteries are going to do a process called equalization, and that's basically an uncontrolled amount of current. Whichever battery has a higher charge, it's going to equalize or basically charge the other battery to the same level. And if you use a depleted battery with a fully charged battery, that is going to be a rapid output of current, create a lot of heat, and could damage your batteries, possibly cause a fire. So always charge them together or make sure they're fully charged when you use them in either of these instances. So we'll go over parallel. Parallel, and if you look, my plus and minus are flipped over on these cells right here, and that's just for the ease of the drawing. I'm going to take I'm going to draw this out here. Parallel is going to look like this. So parallel, they run side by side and never interconnect inside of their own circuit. They only connect at the load. And I will take my negative pole and run him down here. And then same with this. So what that gives us then, our source is two 12 volt batteries at 3 amp hours. So we have doubled our battery power. We've doubled our capacity running them parallel. So now we have essentially one big 12 volt battery with a 6 amp hour capacity. What amp hour means is this battery cell can run 6 amps at 12 volts for 1 hour. If you happen to have 12 amps, that means you will run for half an hour. That's what the amp hour rating means. It's how many amps for an hour. So if you ran 3 amp hours or 3 amps off this battery for at 12 volts, you could run for then 2 hours. Now, our load for the white light is going to be 18 watts. Our total power for the battery is 72 watts, 72 watt hours. So our runtime, just by the math, and it's never going to be that perfect. Our load isn't going to be a perfect 18 watts, and our voltage is going to be a little higher than 12 volts starting. But we're going to do the math anyway. So 72 watt hours divided by 18. 72 divided by 18 equals 4. This would give us 4 hours of runtime by the math. It'd be pretty close to that. We're going to find out our current. We could do the math to see what our current should be. And to do that, we would take 12 divided by 18. And that would equal 0.67 amps at 18 watts. So I have a current monitor and a voltage monitor tied into the test circuit, so we'll be able to see how many watts the light is actually pulling when we're done with this. Now for series, the difference between series is you put, instead of running them side by side, you would tie them together, series, one after another. So we'll make a connection here, here, and we'll draw our line, and we will come in, our positive side goes there, and our negative side will go there. Okay, so this essentially, now that we've tied them together, is a 24-volt battery. Now we've doubled our voltage. That means our capacity is still the same. So since we're using 3 amp hour batteries, we now have a 24-volt 3 amp hour cell, whereas in parallel, we created a 12-volt 6 amp hour cell. Either way, both of them create 72 watt hours. Now, for our runtime, right, we're going to take 72, again, 72 watt hours divided by 18, and we know that equals 4 up here. So we're going to have the same runtime as in parallel, and that is because we have the same energy right here, 72 watt hours. Doesn't matter how we do it, we're still generating 72 watt hours. So the question of, is one of these better than the other? As far as the amount of energy we have to deliver, no, it is not. But there may be an advantage. One particular thing about electricity is the higher the current, the more heat we generate. That's why we're going to do the thermal test at the end to see if there is a measurable temperature difference in the circuit that we can identify. So for these tests, if there was an answer to which setup would be the best option, it would probably be the 24-volt option, only because our circuit would run slightly cooler. And the only reason we can do that is because our light has a variable input from 9 to 30 volts. Generally, it's not this easy. You just need to size your circuit for the appropriate components you're using. So there's not necessarily always, should I use parallel? Should I use series? Honestly, we could do we could use 4 batteries and do 2 banks in series and wire those in parallel, and then all of a sudden we would have 8 hours of runtime. So you can mix and match them both. And another important thing to look at, if you look at the graphical representation, these dots right here where they tie in, if I wanted to take a branch circuit from here to here or here to here, I could still run a 12-volt load off of either of those. And if I just chose one, we wouldn't have to worry about which one of these batteries is going to be depleted faster because of the equalization process. So even though we're pulling off of one, the batteries will equal out the loads themselves, and we will still have the same amount of runtime for each of those cells. So on our bench test, we're going to run, I'm going to create a parallel circuit. We'll measure the current, and we'll find out our actual runtime with the wattage that we find out from our voltage and currents in our circuit. And we'll do the same for the 24-volt series. In my parallel circuit, I'll actually go in after I do the test, I'll go in and wire in isolation switches. That way, if you were to actually use this setup for a work light or something, you would want isolation switches. That way you would not be backfeeding into an open battery case and applying voltage where it doesn't need to be unless you actually have a battery there. So we'll take a look at that as well. But the advantage, if any, the higher voltage is going to create a lower current, which means lower heat in the circuit. And we'll try to take a bunch of measurements. Like I said, I'll build each of these circuits real quick. I've got them set up, so we'll fly through those. And then at the end, I'll just pause the video when I do the thermal tests, and we'll take a look at how much heat each of these circuits is generating. And we'll see how the science and the math actually plays out, and we'll see how accurate the basic math really is. Okay, we'll start with parallel, and I'm going to do wire nuts with the battery adapters themselves, just to show you what it would look like realistically. And then I'm going to take those apart and use jumper wires so we could take measurements and I could show you the differences in the voltage. So for parallel, we would run red with red, and black to black. Since those batteries would be side by side, we would still have 12 volts, and then we would double our capacity as far as the amp hours go. We'll take those apart. For series, we would leave this negative loose, it doesn't matter which one, but then you would tie one positive to one negative, and then you would have a 24 volt cell. But like I said, you could take from this point to this point, make a branch circuit with 12 volts, and the same with this point to this point. Now I'm going to put batteries in them and use jumper wires, and we'll take measurements and I'll show you. We'll be parallel first, so red to red. Black to black. I don't have a black jumper wire. We'll put our batteries in. Turn on the voltmeter. Then at either point, make sure we can see that readout. .24 volts there, and we should have the same here. 12.23 volts there. Okay, so we'll do series next. Just to differentiate, I'll take this green one. And then from there to here, should have 24 volts. 24.48 volts. Okay, but then if I move and I go here, I got 12.23, 12.22. Same if I go to this side. So there's a lot you can do when you wire something in series. You just got to make sure you do it properly. Now we'll stop the video and I'll get the rest of the circuit up here on the table and we'll test that out. Okay, I got the rest of the circuit here and I've already wired up the adapters in parallel. All the blacks go to black, all the reds go to red. Right here I have my low voltage cutoff switch. We're just using this simply for the voltage readout when I put the batteries in. So we'll go through this. This is set for 10 volts. If the voltage of my battery packs drops below 10 volts, it will open up the circuit and then shut off the light to protect the batteries. Here is a DC shunt. This DC shunt is rated for 100 amps. It puts out a 75 millivolt signal that goes to this current monitor readout. And we're going to see what our current is on the light circuit. And that's going to be on the tied into the negative side of our load. And this battery here is simply just wired into power the current monitor. I just did that to make it easier for the video here. And back here we have a graphical representation of the circuit. It looks a lot cleaner this way. So positive side, that's my low voltage shut off, and that's so we're going to power that all the time. These are the contacts for the low voltage shut off, normally open. They power on close. They close on when powered, and then in series to the light on my negative side, this is my DC shunt right there. And anybody has any questions of how a shunt works, I made a video on that as well. Check out my channel. It's a quick 4-minute video. Explains what a shunt is, how it works, and how we use them. But we'll go ahead and plug in the batteries and take our readings and figure out our math real quick. So right there, one battery, 11.9 volts. When we plug in two batteries in parallel, we are at 12.0 volts. And we are reading 0.77 amps. Now, I didn't look. It should not change because this battery is 11.9 by itself. We actually increased our amperage. As our voltage goes down, our amperage will increase because of the relationship between amps and volts and watts. The watts is the portion of the equation that's never going to change. It's going to have a continuous output. So as voltage goes down, our amperage will go up. I'll plug this other battery back in. And 0.77. 12.0 with 0.77 amps. Let's take a look at that. So we'll go 12. I believe it's divided by 0.77. Yep. So our light is rated for 18 watts, but we are actually using or generating 15.58 watts of power off of that light. So it's pretty close, but like I said, when we do the math, it's not as perfect as the math is when we do it on paper. So even though it's rated for 18, we're actually putting out 15.58 watts on that. Now, runtime, we have 72 watt hours. So if we take our 72 divided by 15.58, that actually gives us 4.62 hours of runtime. All right, I'm going to pause the video and set it up in series and see if we can see the differences. Okay, so I've got the bases wired up now in series. You can see the middle. My red goes to my black here in the center, and then I got my red going out to the red here, and my black going out to the black here. Current readout is 0. Obviously, we've got no load. We've got no batteries in right now. So we're going to stick the batteries in and see what that does. And you notice, since it's wired in series, I don't have anything in here, so I'm not completing the circuit. So I've got no readout yet, no output. As soon as I slap this in, everything will start to turn on. Now we've got a voltage of 24.3, and our current, since we now have doubled our voltage, we have now cut our current in half. 0.38 times that by 2, 0.35 is times 2 is 70, so it would be 0.76. So that's the relationship, and our graphical representation is going to be the same. We're just going to swap out that 12 volts for our 24 volts. But that's it. So in series, we double our voltage, we cut our current in half, but what remains the same is the power draw. So we'll take a look at this. We'll do the math again. Bring up my calculator, clear that out. So we got 24.2 and times that by 0.38, or divided by, excuse me. All right, that didn't work out. Or 4.2 times 0.38. No. Okay, I apologize. I did the math wrong. I was confusing myself over there. So back to parallel, we had 12 volts, and we will times that by, multiply that by 0.77 amps, and that's 9.24 watts. That's how much that was pulling in parallel. Now we have 24.2. And then we'll multiply that by 0.38, and we got 9.16 or 9.196. So basically 9.2. That was pretty equal to, yeah, 9.24, 9.2. Okay, so the watts, like I was saying, the watts does remain the same. You just got to do the math properly, correctly, and that's the difference. So 9.24 watts, let's take a look at that. 72 divided by 9.24, 9.2 we'll just say, is 7.82 hours is the actual runtime we would be able to get off of these batteries in this configuration, either series or parallel. So as far as series or parallel goes, there's no real advantage to either. So that's going to be the difference. So now I'm going to hook up the isolating switches for the parallel circuit, and we'll go over that, and then we'll do the thermal test. Okay, so now I've got this wired back into parallel, but I've put isolation switches on each of the batteries. See, my blacks are all tied together and loose. There we go. Don't worry about the red, black, and blue. The red and black are for the 12-volt signal for the illuminated ring. I'm not using that. And the blue is the normally closed portion of this switch. So we're using the normally open, and I tied it into the red, and then on the other side of the contact of the switch, I tied these to the red, going into our low voltage shut-off. So I could turn on one, And I've got voltage 11.9. Then I turn on the second, and we've got voltage there. To verify that, I'll turn off the one, and he's still on. So I could switch between battery packs if I'd like. And if you're not always going to use two battery packs, it would be a good idea to wire in isolation switches. That's how that works. So you see that the current does not change between one or two. Just have them wired parallel. Still 12 volts, but we got double capacity now that we got two batteries. And that's the isolation switches. So what I'll do now is I'm going to shut the camera off, and I'm going to let this run for 10 minutes, and then we'll read the current on the thermal scanner, or read the heat signature on the thermal scanner, and see what we can find. And I'll return. Okay, so here we are. Got the thermal camera out, and right there we're reading 106 degrees about. High spot is 116.8, it says. That's our low voltage shutoff switch. You see everything else is really cool. And this is parallel right now. See, all those wires are really cool. That's a switch. That's one of the isolation switches right there, generating some heat. And then the shunt is putting out a little bit of heat as well. Got a maximum of 88 degrees, it looks like. And then you can see here on the light, try to bring that into focus. Light's putting out 112 degrees. I don't know if that's going to change, but if we're going to see any difference, it's going to be right there at the shunt, or right here on the low voltage shutoff switch. So that's 10 minutes. I'm going to let this circuit cool down, then I'm going to hook it back up in series, and then we'll take another 10-minute run and see what kind of heat we are generating that way. All right, we're back, and we have let this cool down and then heat back up. We're now in series instead of parallel, so we're running 24 volts and 0.38 amps. Looks like our temperature about the same. I think it was 112 on the last one. Uh-oh. Go back to that. My bad. Let's take a look at our shunt. That's running cooler. That was at 88. Now our max is 80. So that is running cooler. And our low voltage cutoff. Put that into focus. It's actually running about the same. I would say measuring the shunt is our best option here to see exactly what's going on. And it is running cooler, so that's enough to show you that increasing the voltage using the same output, that the circuit itself is going to run a little cooler. And that's all I got for you. Thanks for watching.